Welcome to Marshall Lecture 2009. The Marshall Lectures are the premier event that we have at the Faculty of Economics. And the establishment of these lectures go back a long way, and well before, I think, the 1932 when there was the first Marshall Lecturer. And one of the features of Marshall Lectures is that it's open to the undergraduates, graduates, faculty, and other scholars in Cambridge. And we introduced one new thing last year, which I think has been it was a great success. There are exam questions on Marshall Lectures. It's a great pleasure for me to introduce 2009 Marshall Lecturer, Professor Drew Fudenberg. Professor Fudenberg is a Frederick E. Abbe Professor of Economics at Harvard University. He has received his first degree in applied mathematics from Harvard and his PhD from MIT in 1981. After his PhD, he held professorships at the University of California, Berkeley, and at MIT before returning to Harvard, I think, 1993. In addition to being a fellow of the American Academy of Arts and Sciences and the Econometric Society, Professor Fudenberg has been a Guggenheim Fellow and a Sloan Research Fellow. He was the editor of one of our most prestigious journals, Econometrica, from 1996 to 2000, helped found the new, very successful journal, Theoretical Economics, and has served on editorial boards of many leading journals, as well as on the Council of the Econometric Society. He has written a number of books and more than 80 articles in the most prestigious journals. His textbook with Jean Tirole on game theory has been one of the leading texts in the area. His book on learning in games, that relates, I think, to the talk that we are going to have today, is a must for anyone working in the area of evolutionary or learning and game theory, evolution in game theory and learning. Drew's seminal work in this area highlights the crucial roles of informational feedbacks and the precise detail, the extensive details of the game. His work on repeated games show how patient players can achieve cooperative outcomes in a non-cooperative framework. And he's looked at these problems even in the presence of moral hazard, adverse selection, and imperfect monitoring. He has made major contributions to many other areas of game theory and economic theory, including, I've already mentioned, evolutionary game theory, bargaining and renegotiation, theoretical industrial organization, reputation building, social learning, etc. Now, before I hand over to Drew, I just want to make a couple of further remarks about the Marshall Lecture 2009. This year in Cambridge, we are also celebrating the life and work of Charles Darwin, marking the 200 years since his birth and the 150 years since the publication of On the Origins of Species. It's therefore an extra bonus to have as Marshall Lecturer 2009 Drew Fudenberg, who has made seminal contributions to the area of evolution and learning in game theory. Second, in the past we have had many very distinguished Marshall Lecturers. Two of them come to my mind on this occasion, and they are Ken Arrow and Eric Maskin, who both went on to win the Nobel Prize in Economics after their Marshall Lectures. Eric almost immediately. I mentioned this not because of the Nobel Prize. I mentioned this because Eric was Ken's student, and Drew was Eric's student. Therefore, for the first time, we seem to be having a family tree for the Marshall Lectures. Last, I should add that given my interest in economic theory, it's a very special pleasure to introduce Drew, because over the years, I've learned so much from Drew's work.
Thank you very much.
Drew.
Thank you, Hamid. Thank you, everyone. It's a great honor and a pleasure to be here. To talk about learning equilibrium in games. And despite the fearsome words about examination questions from Professor Saborian, I was also advised to make these lectures accessible to a general audience. So the lectures today will be quite non-technical, no equations, symbols, or anything. There will be numerous references to work, both mine with co-authors and many other people's. And on the Marshall Lectures website, you can find a list of the references that I'll be discussing. Another preliminary, we're going to have a bit of fun and actually play a game at one point. And for that purpose, it's possible for people in this middle section to scooch either this way or that way, so I like it to be clear whether you're on my left or on my right, and leave a gap. If it's not enough space in the middle, perhaps some people could move over, off to the wings. But I'd like to, so pick a spot, everyone. Are you a left or a right? Because we need to be able to see. Okay. It's not as straight a line as this one would like, but we'll make do when the time comes. And also, you all should have been handed some pieces of blank paper when you came in. So we'll be using that when we do these games. So those will be, and if you, I didn't think to ask for writing implements. If you don't have access to a pen or pencil, maybe you could plan on borrowing one from a neighbor. So we don't need it quite yet. So game theory. Game theory is a study of interdependent decisions. It's decision making when the payoff to the action can depend on the actions of others. So put that way, it sounds quite general. And it is quite general. Game theory has been used in all areas of economics, industrial organization, which Hamid mentioned, but trade, macro, labor, development, but also other fields. It's used in political science to study voting and lobbying, anthropology, sociology, and apropos of Darwin, it's used to study biology as well, and we'll be seeing that today. Okay. So the distinguishing feature of games is that the optimal action for a given agent can depend on the actions of the others. So then there's no unique optimal action. It depends on these expectations. Well, how do we resolve that problem? How do we predict what will happen in a game? The standard methodology in applying game theory to real-world problems is to assume that the outcome of the game will correspond to one of its Nash equilibria, or perhaps to some particular subset of a Nash equilibria we think have some claim to precedence. But that raises the question of when and why does that make sense? When should we expect play will actually look like a Nash equilibrium? Well, from the viewpoint of a learning in games literature, equilibria are the result of some sort of non-equilibrium dynamic process of learning in a literal sense, or more generally some form of adaptation and response. So this theory of learning in games helps explain how and which Nash equilibria will arise. How Nash will arise, and moreover, which ones. It explains that quite well in the class of static simultaneous move games, the games where each player takes a single action and then the game ends. It turns out that if we move beyond the setting of simultaneous move games, then learning theory suggests perhaps Nash equilibria aren't the objects of interest. We should be looking at other sorts of equilibria. So what I plan to do in these lectures, today I'm going to focus on these static games where Nash equilibrium does seem like the right equilibrium notion. I'll give you my take on game theory and Nash equilibrium, talk about learning in static games, and then digress a bit to do some evolutionary game theory in biology. Then we'll move on from there to extensive form games and the outcome of learning in extensive form games, and these other equilibrium concepts that you probably haven't heard of, self-confirming equilibrium, subgame confirmed equilibrium. I'll explain all that next time. And if you don't know what an extensive form game is, I'll explain that next time too, perhaps the end of lecture today if there's time. So game theory. I said game theory is really general, interdependent decisions. That's almost everything. If you put it that way, you think people should have been talking about it for a long time. And they have been, depending on how charitable you are, how much you read between the lines. We can trace back the origins of game theory to different places. I think by the time we get to Hume and Rousseau in the 1700s, there's verbal descriptions that, with a little bit of generosity and interpretation, we can call game theory. But they weren't formal. The first formal analysis of a game that I know of is Cournot's analysis of a duopoly model. This is a model of price setting in a market with only two firms. If it's only two firms, then perfect competition doesn't make sense. We don't want to say that the firm neglects the effect of its decisions on the market price. Okay? So suppose the firms know the demand function. They know how the price will vary with output. But to choose their output, they also have to know the output of the other firm. How do they know that? Well, in Cournot's model, the two firms simultaneously choose their outputs. Given the outputs, price somehow emerges to clear the market. You think of a Walrasian auctioneer, if you're an economist, or some bidding process. He's quite vague on the details. A Cournot equilibrium is a pair of outputs, one for each firm, such that each firm's output maximizes its profit given the output of the other firm. That's an equilibrium in the sense that neither firm has any incentive to change. If for some reason each firm is making the Cournot output, neither firm has a reason to change. Now, Cournot was not an economist. There really weren't economists then. He was a chemist, a physical chemist. And he thought of equilibrium by analogy with equilibrium of a chemical process. And he actually proposed an explicit dynamic process by which the players could adjust their outputs. And the steady states of his process were precisely the equilibria that he was defining. So in that sense, he was the first person to do learning in games. So it's a very important precursor of what I'm talking about. The specific assumptions he made are perhaps not so realistic. He assumed that firms took turns picking outputs. Each time the firm maximized profit, believing that its opponent's output in the future would be the output it made yesterday. Okay? So you see firm one's output, firm 2 does something, firm 1 responds, firm 2 responds. It keeps on flipping. If they started out believing their opponent's output was constant, very quickly they should be disabused of that, because the outputs, unless you happen to start at the equilibrium, the outputs aren't constant. So this is maybe not the best model of learning in games, but it's the first. So following Cournot, a number of other games were analyzed as special cases. Bertrand said firms don't choose prices. Outputs, they choose prices. Okay? They choose prices simultaneously, commit themselves to supply all possible demand to those prices. They have constant marginal cost. Okay? Find a Bertrand equilibrium. Edgeworth said, firms have capacity constraints. Sure, they set prices. They can't really make infinite output. There's some amount. So let's reanalyze the game. He had an Edgeworth equilibrium. Hotelling looked at a model of firms choosing locations as a metaphor for product differentiation. So each of these were one-off examples, what we now call games. Each of their equilibrium concepts, the Bertrand equilibrium, Edgeworth equilibrium, Hotelling equilibrium, are all examples of what we now call Nash equilibria of the various games. Okay, so Nash came along and generalized all this past work. But before he did that, there was very important work by von Neumann on the min-max theorem, and then this book, von Neumann and Morgenstern, called The Theory of Games and Economic Behavior. It's a hugely important and influential book, remarkably ambitious. Okay? And here's a quote from the book. We hope to establish that the typical problems of economic behavior become strictly identical with the mathematical notions of suitable games of strategy. So it's all of social science, economics is going to be this mathematical formalism. So it's, as an applied mathematician, this sounds wonderful to me. The book gave the first general definition of a game, which generalizes Cournot, Bertrand, and so on. It defined extensive forms and strategies. So a strategy in their book is no longer simply an output or a price. It's a complete contingent plan. So it can say what you do in every eventuality, in every state you might encounter. So we'll come back to this idea of strategies tomorrow when we talk about extensive form games. So it's a great book, brilliant, played a pivotal role in, I think, encouraging the mathematization of economics and social science. But it has, the reason I'm talking about it is not just that it's a great book, but I think it was fundamentally wrong-headed in an important aspect. So they had a very different interpretation of equilibrium than the one I'd like to convince you of. So and it was different than the view of Cournot or Nash. So von Neumann and Morgenstern saw game theory's task as providing, quote, mathematically complete principles which define rational behavior in a social economy. Nothing about long-run outcome of dynamic processes. Rationality or super-rationality. People are rational. They know everyone else is rational. They know it. Everyone knows it. It's common knowledge. And they wanted these predictions to have a unique, unambiguous prediction in every game. So in two-player constant sum games, von Neumann's min-max solution does exactly what they're looking for. But as economists, most of the games we care about are not constant sum. So constant sum game means anything player 1 wins, player 2 loses. So in a constant sum game, we can't say which outcome's more efficient. Everything's equally efficient. So it's a pure conflict model. It's not without interest, but it's a very small set of the games we care about. So the problem with their program, first of all, a unique prediction is too much to ask for. Secondly, their assumption that they wanted to base game theory on was that people are rational. But rational behavior, or even common knowledge that everyone's rational, does very little, or can do very little, to restrict the set of possible outcomes. You can't go from rationality to unique predictions. And we'll see that. Okay, and even common knowledge of rationality isn't enough. So we need some other way of predicting what will happen. And that's the sense in which I think the book was wrong-headed. I don't want you to think of equilibrium as a result of super-rationality. Okay? Because that's So Nash defined what we now call Nash equilibrium. So let me tell you what it is. I said it generalizes Cournot and Bertrand and so on. So the primitives of this definition are things called strategies. But think of these strategies as being outputs in Cournot or prices, or better yet, you're a subject in a game theory experiment, you're sitting at a computer terminal, you've got some keys. You can push A or B or C. Okay? These are keys the buttons can push. Think of each player pushing their button. They're in these little carols sitting at a computer screen. There's little dividers between each person, so you can't see what other people are doing. You all make your choices simultaneously. A strategy profile is then just a specification of what each player did. So each player 1 did, what player 1 did, what player 2 did. And now you see this word player role on the screen that may be a bit puzzling. What do I mean, each player or player role? Well, we could have a game with player 1 and player 2. And it might be the case that people on my left were all player 1s, and people on my right were all player 2s. Okay, so that's what I mean by these roles. But this is what will be happening quite soon. So a game in strategic form is simply a collection of sets of strategies. Here's the buttons player 1 can push. Here's the buttons player 2 can push. And a payoff function. And the payoff function has to say what the player's payoffs are, for each combination of buttons. And a strategy profile is a Nash equilibrium if each player's strategy, each player's choice of button, maximizes that player's payoff given the strategies being used by all the other players. So just to repeat that in different words, no player can get a higher payoff by changing their strategy, holding fixed the strategies of everyone else. The thing to notice, these Nash equilibria are consistent predictions of play. The sense that it wouldn't be consistent for all of us to predict some non-Nash outcome. If we all were sure the outcome was going to be this thing where the player 1s played up and the player 2s played 7, but it turned out that given the 1s played up, the 2s could do better with 8 than 7, then there's something wrong there, because everyone should know the player 2s wouldn't really do that. So if we get the Nash equilibrium consistent, if we get there, you think they might persist. But that doesn't tell us why we should get there, right? So if we're at a Nash equilibrium, no one has an incentive to change. Okay. Here's a game. Okay. The way games, two-player games are commonly depicted, player 1 chooses rows. So here player 1 can choose up or down. Player 2 chooses columns, either left or right. And then in each element of the matrix, we have two numbers. The first number is player 1's payoff at that outcome, and the other is player 2's. Okay? So what I'd like you to do is interpret this 5 as 5 pounds. I don't have a pound sign on my math type program. And we're going to play this game. Okay? So I'd like each of you to take one of the pieces of paper that you have, write down your name. Okay, so people, and here we need this division. People who were player 1s should please write down either an up or a down on their piece of paper. People who are player 2s should please write down either a left or a right. I'd like you all to do this. We will then collect the pieces of paper, and we will pick one player 1's and one player 2's form out of a box, and we will pay off in pounds the resulting choices. Okay? So I'm not asking you here to engage in a theoretical exercise. I'm asking you to try and maximize your chance of winning the 5 pounds. Okay. I'm also asking you, so please just don't talk to each other. It's important for the validity of this experiment that if there's any confusion about the rules, ask me. But please, you can talk to each other and ask for pens or pencils. That's fine. But otherwise, please don't. And once you've made your choice, so these two, so player 2s, please pass their choices here. Player 1s, please pass them there. Okay, does anybody need more time? We all set? Okay, so let's go. So everyone is done. We're just handing these in. So please pass them down the aisles. And I know this is distracting, but I'm going to try and keep on talking while we collect the data. Okay, so if you look back at this game has two pure strategy Nash equilibria. One of the Nash equilibria is all the player 1s play down and all the player 2s play left. And then everyone gets 5 and they're happy. A second Nash equilibrium is all the player 1s play up and all the player 2s plays right. And again, they all get 5 and they're happy. This game also has what's called a mixed equilibrium. If it turned out that half the player 1s played up and half the player 1s played down, then the player 2s were just indifferent about what to do. So we can imagine a state where the player 2s in the front half of the room, if it's assuming that's half of you, played left, and the player 2s in the back half of the room played right. Okay? And if that was about 50-50, then the player 1s are roughly indifferent. So we could have a situation where even though each individual agent is making a choice up or down, the distribution looks mixed. This is what's called a mixed strategy Nash equilibrium. Okay. Note, though, if player 1 expects up, comma right as the outcome, player 2 expects down, comma left as the outcome, what happens, then player 1 plays up and player 2 plays left. It's not a Nash equilibrium. So basic point, you can't mix and match Nash equilibria. Down left is an equilibrium. upright's in equilibrium, but we can't take player 1's piece of equilibrium number 1, player 2's piece of equilibrium number 2, and put them together and get an equilibrium. So that shows us that when there's multiple equilibria, the outcome won't look like any of the equilibria unless there's some way that the players expect the same equilibria. Because everyone should put in their choices by now. So, Brioni, would you please pull out, or need 2 people. One person pulls from one box, one person pulls from the other. Okay, so what are the choices and what do we have? And who are there? If it's a 0, we don't have to announce the names. If we manage to get to 5 pounds, we should announce the names. It's up and right, and so we have 2 winners. So who were they? Hand, please. Adam. Don't be shy. Okay, and. Very good. Okay. So thank you. So please hand out the envelopes. Okay. And then tabulate the results for me. Okay, we're going to report into you soon what the total distribution was. That's going to take a few minutes. But the example shows you, so to get at Nash equilibrium, we need some coordination and expectation. So it happened that one time. I think if we pulled out 2 more, it's no guarantee. We'll have to see what the numbers are like. Coordination is not an implication of rationality, and rationality does not imply equilibrium play. So the assistants are tabulating the results. Once we have them, I'll report them to you. I'll tell you how many player 1's played up, how many played down, how many played left, how many played right. And then we're going to play it again, the same game. But to speed things up, we're going to play it with a different protocol, a different way. I'm going to ask you to think of your choice and mentally write it down, commit yourself to it, and then we'll do it by show of hands. Okay? And then instead of picking papers out of a hat, I'm going to pay you sort of the expected value. What do I mean by that? Instead of paying you 5 pounds if you match, I'll pay you 10p for each of the 5s you get. So each of these 5s are now 10p. Instead of playing 1, if your name is chosen as a player 1, instead of playing against a given player 2, I'll match you against every single player 2 in the population. And against each one, you'll either get 10p or 0. And we'll add it up. Okay? So that's a notional idea. The dollar amounts won't work out so tidily there, so I'm not going to pay that one off in actual money. It'll be a thought experiment as opposed to an actual experiment. So, okay. So, but before we play it, let's just think of it. I mean, well, okay. What do we think would happen if we showed hands? And I reported the scores. And then we showed hands again and showed hands again. Okay, so I'm going to give away the punchline and tell you that I don't expect that every single person played up and right in this first round. But I expect that if we played the game often enough, we would end up either at up, right, or down left. And I can't tell you which because I haven't seen the data yet. But that's what I expect. And that's really the point of learning in games. It's simplest in static games. Oh my. Okay. Going to look at self-interested players. So these aren't players who are trying to get to equilibrium. These are players who want to maximize their payoffs, like you just did. We want to have some model of this learning process. And there's no point in explaining equilibrium in my simple matrix game by saying, well, assume equilibrium of this adjustment game. That's just leads to a regress problem. Helps us not at all. So we're going to look at non-equilibrium learning. What does that mean, non-equilibrium learning? It necessarily means that we have to allow for the fact that some players' learning rule, how they update on the basis of data, might not be optimal given the rules of all the others. Why must we allow for that? If we rule that out in principle, say each player's rule is optimal given the rule of the others, what have we said? We've said there's an equilibrium in adjustment rules. So why should that be? Why should I know anyone else's adjustment rule? Okay. So instead of asking no one makes a mistake, we'll ask that no one makes stupid mistakes or implausible mistakes, mistakes that aren't too hard, mistakes that are easy to spot. There's many different adjustment rules in the literature. I'm going to focus on belief-based models. Agents form expectations about the play of their opponents. Use those beliefs to choose their actions, as in models of fictitious play and smooth fictitious play. I won't present the details. There's three key features of these models I'd like you to think about. These models involve passive learning, that agents' actions have no impact on what they see. So that was true when we pulled two names out of a hat. It'll be true if we all raise hands. You'll see the hands raised regardless. So that means there's no reason to change your play to gain information. There's no experimenting in these static, no reason to experiment. Strategic myopia. I want to have people learning, so I want them to play repeatedly. But I don't want them choosing their play now to influence the play of their opponent in the future. Because then we wouldn't have people learning to play that matrix game. They'd be learning to play a repeated game. You might think, I'm going to give up some payoff now in order to change the way my opponent plays. It'll be nice to me later on. So I'm going to assume the strategic myopia. Why might that make sense? Well, it makes sense in large populations like we have here. There's many agents in each player role. There's many of you player ones and many of you player twos. If we're playing this game 10 times or 100 times, there's not much reason for one of you to say, gee, I think they're playing right. I should play up, but I'm going to play down because I want to teach them something else. Why is no reason to do that? Because you're a player one. There's 50, 100 of you. Your play isn't going to have much influence on what anyone sees. So it's simply not worth your time distorting your play to change people's play in the future in a large population. There's two sorts of large population models that one can think about. The one that's used in most experiments is called anonymous random matching. So what that means is we have all the subjects at these carols. We pair up the play of a given player one with a given player two. They don't know each other's names. Next period, they're rematched. So this first treatment we did with the boxes, that was roughly anonymous random matching. We took Adam's name out of one box, Coombs out of the other box, and there they were. And we could, if I had enough time, I could have pulled out a second pair and a third pair. We put them all back in. Next time, if we played it again with the paper, there's no presumption the same two people would be paired. Okay, it's random matching. The other way of thinking of large populations is each period, all the agents play. And at the end of the period, we report how many player ones played up, how many player ones played down. And the payoff of an agent depends on this aggregate distribution. So that's what I'd like to do the second time, but I need the data from the first time. How's the count coming? Are we nearly? Okay, so please let me know. Okay. And the last property we need, or I'm going to assume, is called asymptotic empiricism. It simply means that people's beliefs eventually converge to the time average of what they've seen. Okay? So at the start, I don't know what players believe. Okay? But as players get more and more data, we think that their beliefs end up looking like the data with a large enough sample. So in particular, if the time average of play converges, so if it turns out that we play it over and over, and eventually all the player twos are playing right, then the player one should eventually decide, yes, the player twos are always playing right. Okay, so the beliefs should end up matching the data. Motivation for this, other than simple plausibility, suppose agents were Bayesians, and they believed that the distribution of opponents' play was some fixed random variable. So you say, I don't know if the player twos, if 2/3 of them play up, or 1/3, or 3/4, but I had some beliefs about that. So if you had those beliefs in your Bayesian, then you'd eventually have your beliefs looking like the data. That's an explanation. Note, though, suppose agents are all myopic. Each day they maximize that period's payoff. And asymptotically empirical. Then, in fact, the aggregate distribution of play will not, in general, be stationary unless we start at a Nash equilibrium. Okay? So, unless we start at equilibrium, acting as if the environment is stationary is making a mistake. Is that bad? Well, it certainly means it's not a Nash equilibrium in the adjustment rules, but I claim stationarity can be a reasonable first guess about what's going on. If you don't know much, any evidence to the contrary, think the world is stationary. On the other hand, if you're given evidence to the contrary, you might reject it. So suppose that you're playing matching pennies, and you see your opponent's play has been heads, tails, heads, tails, heads, tails, heads, tails. Okay, this very simple deterministic two-cycle. Well, if you're asymptotically empirical and you thought the world is stationary, you say, gee, it's 50-50 he plays heads or tails next time. But that'd be sort of thick, right? You think if you saw this sort of sequence, you might think, well, he's been alternating, he just played tails, I think he'd play heads. So given some sort of data, this is a bad assumption. So I mentioned these two processes of fictitious play and smooth fictitious play, but I didn't define. But I said they had these properties of asymptotic empiricism and strategic myopia, and passive learning. So it turns out with the first of these processes, the fictitious play, you can get this sort of fast cycling, which I think then, in that case, the belief model doesn't make sense. But the smooth fictitious play says people respond in a sort of a smooth way to their beliefs, and then in fact, you can't get this fast cycling. Okay? So the system needn't be stationary, but suppose that it's spiraling into a steady state, moving slower and slower. Then it's true the system's not stationary, but it's almost stationary. And there's some periodicity which is getting longer and longer and harder. So maybe then acting as if it's stationary is not such a bad assumption. So that's my defense for supposing that agents act as if the world is stationary. Okay, result, with asymptotic empiricism and myopia, if the population converges to everyone playing the same strategy, that strategy must be a Nash equilibrium. So that's a sense in which this learning explains Nash equilibrium in these static games. And the proof of this is very straightforward. If the aggregate play in the population converges, the player twos end up all doing all right. Then the player one's beliefs have to converge to a distribution, have to converge to the twos always play right. And then if what the player ones is doing isn't a best response to the player twos, they should change because they're myopic, they're playing a best response to beliefs. Beliefs look like the truth, so the thing would fall apart. Okay, so let me type this in. Let me find the, okay. So how many player ones played up?
89.
And how many played down?
52.
I didn't hear you?
52.
52? How many player twos played left?
58.
And how many player twos played right?
75.
Okay, so now you've all seen this. You all know that you've seen this. Suppose that we're going to play this game again. And what you're going to get is, 10p for each of the positive entries of the other sides. Everyone understand what I'd like you to do? So take 10 seconds. You're still player ones. You're still player twos. And just keep the piece of paper. If I have time, I'm going to use it for something else. But mentally commit yourself to a choice. Okay. Everybody set? Okay, so player ones who chose up, raise your hands, please. Okay, I'm not going to count. That's like virtually all. Player twos who chose right, hands, please. So it's okay. So here we converge to Nash equilibrium in 2 rounds, basically. The first round, this is not a Nash equilibrium, right? This isn't the mixed equilibrium. It's a bit of a tip towards upright, but hardly overwhelming. We gave you data, and now Nash equilibrium. So that's a perfect example of what I'd like you to think about. Okay. So I have some more things to say about how history and culture can help people coordinate. And maybe I'll come back to that. But I want to get to the biology first. So some comments. The assumptions I made for this result that if we converge, it's Nash, were that we had asymptotic empiricism and strategic myopia. Well, neither of those assumptions requires that players know game theory. Okay? Play can converge to Nash equilibrium even if the agents have never heard of Nash equilibrium, simply maximizing their own payoffs. That's analogous to the fact that consumers don't have to take economics classes for competitive equilibrium to describe what happens in competitive markets. Okay. So the part that I may skip over is this idea of people don't play the same game very often, but you can sometimes play one game and use it to learn about a different game. And that's almost unavoidable. If you insist that every instant of your life is different than every other instant, you can't learn anything. You've got one data point per second or per millisecond. Any learning involves some extrapolation. I think people do extrapolate between games, and that links to Schelling. But I really think, especially given the mention of Darwin, I should be sure to get to that while I have time. So not only do players not have to know game theory to get the Nash equilibrium, they don't have to be rational. They don't even have to have memories. Okay? And that's shown by work in evolutionary game theory. It's nice to mention that because of a Darwin tie-in, as Samid mentioned, but also it's important to mention that because I often hear the following syllogism, or attempted syllogism. Game theory assumes agents are perfectly rational. Agents aren't perfectly rational. Therefore, game theory is irrelevant. Okay, so this has been written more or less baldly in all sorts of places. It's simply false, because there's no presumption of rationality in evolutionary game theory. Evolutionary game theory, the payoffs of the agents corresponds to reproductive fitness. And the players are genetically programmed to play different actions, or if you're a biologist, you say it's not actions, it's phenotypes. They're programmed to express given phenotypes. Fitter strategies or phenotypes have more offspring, so their share of the population increases. Now, what makes this evolutionary game theory, as opposed to just evolution, is fitness now, I'm assuming, is not absolute but frequency dependent. So the fitness of a given action or phenotype can depend on the overall frequency distribution in the population. Okay? So survival of the fittest now is inherently game theoretic. Okay, there's no, in the coordination game, what was fitter, up or down? Right? It's a meaningless question. It's up is fitter in an environment where the player twos play right. Down is fitter in an environment where the player twos play left. So there's different ways one can look at evolutionary game theory. The standard, simplest process is called the replicator dynamic. It assumes that there's a single continuum population. So instead of n people, there's a unit mass. And it's a deterministic adjustment process, not random, in continuous time. That's very stark. There's all sorts of variants. Chris Harris and I did a paper on replicator dynamic when the fitness function is stochastic. So there's wet years and dry years, and what's fit depends on the weather. You can look at replicator dynamic in discrete time, say, instead of being continuous time for seasons. All the animals reproduce in the fall each year. Finite population models, etc. There's some references on the reading list. The state of a system is the fraction of agents using each action. So 1/3 the player one's playing up, or 1/3 the players play up, and 2/3 play down. The reproduction rate of the individuals is their payoff in the game. So we identify payoff with reproduction rate. So that means the total number of offsprings at a given time of the agents playing A is the product. We see how many people are playing A. Half the people play A. And what's the payoff of A? Each A has 2 children. Okay? We could then show that the fraction of the population that plays A grows only if the current payoff to A is higher than the average payoff in the population. So strategies who share are doing better than the average, their share grows. Strategies doing worse than the average, share decreases. At a steady state, every action that has positive population share must be equally fit. Why is that? If we have 1/3 of the people playing A and 2/3 B, but A is fitter, the share of A is growing, so it's not a steady state. Steady state just means a stationary point where the system's not changing. So at a steady state, if every action is being played, the steady state must be in Nash equilibrium. It must all be equally fit. There can be other sorts of steady states that are not Nash equilibria. Why? Because in this very simple, stark model, non-existent strategies have no offspring. Right? So it doesn't matter what great score A gets. If everyone is playing B and B gets payoff 1, A gets payoff 2, but not a single person is playing A, there's no force for the share of A to grow. There's no mutations in this model, which is sort of odd for a model in biology. It's simply too stark. Okay? So one observation, suppose there is some small mutation that perturbs the state a bit. Then if we're not currently in a Nash state, we'll move away. So non-Nash steady states are not locally stable. If some small number of agents started playing, so we're at a steady state. Everyone's playing A. A is not optimal against itself. B would be better. No one's currently playing B, so it's a stable point. Some small share of people starts playing B. They're doing better. Their share grows, so we move away from the state with all A. So that motivates the idea of an evolutionarily stable strategy, or ESS. Oh, I claimed there was no notation today. Well, we're almost done. So it's just these two slides, okay? It's not economics notations. Maybe that's okay. Suppose the population is originally at some profile sigma, and some small share of mutants start playing some other strategy, sigma prime. Then ESS asks that the existing population gets a higher payoff against the resulting mixture than the mutants do. So we have these mutants, we have this mixed population, okay, and if the existing thing does better, the mutants die off. If the mutants did better, then their share would grow. So here's a formal definition of ESS. A strategy is an ESF if it's a Nash equilibrium, meaning that, oh my, more notation, utilities. No other strategy, sigma prime, does better against sigma does than sigma does against itself. That's just a statement of Nash. And moreover, if some sigma prime mutant could do as well against sigma as sigma does against itself, so sigma prime is an alternate best reply, then the mutant against itself does worse than the old strategy against a mutant. So that's a complicated definition, so the advanced students can take notes and be ready on this, and the rest of you could ignore that, because for purposes today, the important observation is that any strict Nash equilibrium, a strict equilibrium is where the equilibrium is strictly better than any alternative, given the state. Any strict equilibrium is an ESS. And for typical static games, all the pure equilibria are strict. So if we ignore those mixed states and think only about pure states, then typically, you can read evolution biology papers perfectly well. Every time you see the word ESS, cross it out and put in Nash. And there really is no difference on this class of games. So ESS has been used in explaining, or Nash, because it ends up being always the pure equilibrium that they use, it's been used to explain a wide variety of biological facts. Examples include mutualisms and parasites. I've been talking with a woman at Harvard who has a lab where she has little shrubs and ants. And the ants are symbiotes with the shrubs. They help protect them from predators, and the plants make little feed pods to feed the ants. I'm trying to understand that. There's animal behavior such as territorialism, why animals will defend their territory, other animals go away. But the one I wanted to tell you about, I thought of all the many applications, the one I find most intriguing, because it's the most startling to me, it shows the breadth of game theory, is we can use ESS to explain genomic imprinting. Okay, so what is that, you ask? Humans and most animals inherit 2 copies of most genes. One from the mother, one from the father. And for most of the genes, both copies are functional, meaning they both are expressed. They both get proteins produced. For imprinted genes, production of the corresponding protein occurs only from one of the two alleles, either from the maternal or paternal allele, depending on which parent passed on the gene. And examples of this are in insects, mammals, and plants. And in mammals, this happens most often with genes that control placental growth and development. So we have these genes that control these factors that make the embryo grow quicker. And whether or not this gene is turned on and working depends on whether it was inherited from the mother or the father. This is genes in the embryo. Okay? So how do we explain this? Well, David Haig has an explanation. This comes from conflicting interests between the father and the mother. And what makes this intriguing is the game here is played not between the father and mother per se, but between the genes of the father and the genes of the mother. So why conflicting interests? Well, I mean, if the pair was completely monogamous, and if they both died at the same time, there wouldn't be conflicting interests. But to the extent that the father might have children from a mother other than this one, the interests aren't precisely aligned. And if the species is particularly promiscuous, the interests aren't so closely aligned at all, because the father may not have any more children with this mother, so the father would like the mother to invest a lot of resources in the current child. Who cares about her health and the future children, because he won't be around. Okay. So in Haig's model, individual has a maternal and paternal allele that control this factor which controls the growth of the embryo. And suppose that the total amount of this growth factor is the sum of the amount produced by the maternal allele, call that M, and the paternal allele P. Okay? So if X makes the embryo grow, that eats up maternal resources. And as I said, unless the mother and father are completely monogamous, then the mother and maternal allele will favor a smaller amount of this growth factor than the father will. Okay? So suppose that the maternal allele favors an amount capital M, and the father gene would like some P greater than M. Then it turns out that the ESS of the game is for the alleles to produce P if they come from the father, and 0 from the mother. So you can see that coming. If it's coming from the mother, you know what the father's gene is making too much anyway. I don't want any. Okay, so this is a result that explains why. The thing about imprinting, which is interesting, it's typically a 0 or 1 phenomenon. I mean, either both genes are on or one is on, the other's off. It's not part way on, it's all the way off. So that's genomic imprinting. We can take this a bit further. You say, well, so if the father is making this embryo grow too big, mother doesn't like it, what could she do? Well, in principle, she could produce some buffer chemical that soaks up this growth factor so that the embryo does not grow as much. Okay? And in fact, there's evidence that this happens, that there are species of mice where you have these arms races. And in fact, there's 2 similar species of mice, where one is much more promiscuous than the other. Okay? So in both species, you have sort of normal, healthy children that pop out about the right size with not too much infant mortality. But in the monogamous species, there's comparatively low production of this growth factor and of the buffer. And in the promiscuous species, there's a high production of both the growth factor and the buffer. Okay? And those are both equilibria. If you crossbreed the animals, it's a disaster, because either you get lots of growth factor and no buffer, and the thing grows too quickly and the mother dies, or you get little growth factor and lots of buffer, and the fetus fails to develop and dies. So it's very interesting. Game theory works not just people competing, not just bacteria competing, but even within the organism, you have equilibria between mother's genes and father's genes. Okay, so that's my homage to Darwin and evolutionary game theory. There's a huge, huge literature on applying game theory to biology, which I think is fascinating. So I guess I have 5 minutes left, and I could use the time to, well, I'm going to do a teensy bit to close this loop, and then I'm going to play one last game. I think we barely have time. Okay. Back to belief-based learning, I mentioned the replicator dynamic and stability and instability of equilibria. With belief-based learning, we can also study stability and instability of equilibria. So this left-hand game has the 2 pure equilibria, up left and down right. There's also a mixed equilibrium, but we feel it's unstable, just like in the asymmetric game that we played. We think that if we got a bit more people up left, we'd spiral there, and a bit more in down right, we'd spiral there. And that's true. So one can show that this mixed equilibrium is unstable in belief learning. So it's a Nash equilibrium, but it's not realistic. On the other hand, this game on the right is a representation of matching pennies. Player 1 wants to match player 2 wants to anti-match player 1. So here there's also a 50-50 mixed equilibrium. If player 1s play 50-50, 2s are indifferent. It turns out this stability here is less obvious. It turns out that it is stable under belief dynamics. So this was an example of what I was saying at the start, that the belief dynamics not only explain Nash equilibrium, they can tell us which ones. Sometimes the mixed equilibrium is stable, sometimes unstable. Okay, there's formulas and results on the slides. It's not so much fun. Let me do one last thing for fun, and then invite you to come back next time to hear about learning in extensive games. So I'm going to play the following game. Okay, each of you is going to write down an integer between 1 and 100. Don't do it yet. And we're going to then see what the numbers chosen were. I'm going to need some help with this. I don't have a board to tabulate, but we'll do this. And we'll compute the median. The median is the number where half of you are above and half of you are below. We'll then compute 2/3 the median. The winning player or players are the ones who are closest to 2/3 the median. So, and there's a calligraphy error there. The winner's payoff is 10 pounds, not $10. So if it's a single winner, the winner gets 10 pounds. If there's 2 winners, you should get 5 pounds and so on. Does everyone understand the rules? Okay, so once again, I'm not asking you to compute Nash equilibria or prove a theorem. I'm asking you to try and win 10 pounds. So you think about what you think other people will do. Okay, I'll give you 30 seconds because we're a bit pressed for time, and then we're going to do this. Everyone, please write down their name and an integer. Do you have a spare pencil? I ought to have brought one. Thank you very much. No, we need the whiteboard or something. Okay, but no, we aren't collecting these. Okay. Everyone written their choice down? Okay, so the reason I'm doing this with the median is we can actually compute. Everyone done? Please, okay. We can work out the outcome here with show of hands. So how many? I need some help counting though. How many people chose 50 or higher? 50 inclusive and higher. Okay. So please count that for me. 50 and higher. Okay. How many chose 40 to 49? I didn't hear you? 12, 13, okay. So how many chose 10 or fewer? Maybe we should collect them. This is slower than I thought. It's a big group. We need one person counting. What we should do is Brioni, maybe you could count the right-hand side, he could count the left-hand side. We have three of you, each of you count one group, as opposed to triple counting. Total? 51 in the whole room. Of those two. Okay, so how many were there? Huh? I don't understand. Okay, 75. Okay, that's under half. Okay. 20 to 30? Or 20 to 29? Yeah, you guys count different pieces, please. That's, we do. $15, $14? So 27, 36. So it's going to be somewhere between 10 and 20 is the median. How many? When I said 10, was it 10 inclusive and under? Or, yeah, it was 10 and under, wasn't it? So that's 11 to 15. Okay. And 16 to 19? Can't be that many. $86. Okay. 13 and 14 only. 13 and 14? Okay, hardly any. Okay, 11. So 12? Is everyone? Okay, so I make out 12 is the median. 2/3 of 12 is 8. Okay, so how many people chose 8? Hands, please. One? Only one? Okay. So this is an example of what's been called a beauty contest game in reference to Keynes's comment about the stock market, that the point was not to pick who was prettiest, but who everyone else thought everyone else was prettiest. It's also a game where most common definitions of common knowledge of rationality would say everyone should pick one, which is the unique Nash equilibrium. So if you picked one, you picked the Nash equilibrium, but I didn't ask you to pick the Nash equilibrium. I asked you to try and win 10 pounds. Okay? So I claim if we played this game again, the winning bid here was 8. So even without the lecture, if we played it again, I think the winning bid would be lower. Would it be 1? It might be 3. It might be 4. If we played it a few times, we'd end up with Nash equilibrium. So this, again, illustrates my theme, Nash equilibrium. There's no reason to expect Nash equilibrium the first time people play an unfamiliar game or a game with people they don't know. Nash equilibrium arises from learning, not from rationality, does not describe initial play. So hopefully I'll see most of you tomorrow then.